My name is Thomas Carnahan, and this is the first of 3 papers for my Assignment 3 for Complex 529-21B Engineering Self-Adaptive Systems. The title of this paper is IAS, an IoT Architectural Self-Adaptation Framework. The authors of this paper are Moghaddam, Eric Rutten, Felipe Lalanda, and Giraud. The venue is European Conference on Software Architecture, ECSA 2020. The focus of this paper is managing renewable energy sources, specifically wind farms. Wind farms are hard to predict, and the generation of them can cause overloading if not managed properly. This can be avoided using circuit breakers to limit the current coming from the wind farms. Batteries may also be used and will charge up during times of peak generation. A variation of Internet of Things sensors, actuators, and processors may also be used to limit current coming from the wind farms, but this introduces issues with reliability and performance, specifically sensors going down and causing major issues in the system, or too long response times caused by too many sensors or issues in communication between sensors. Another thing that may be done is the disabling of power lines, but this massively increases cost on the system. There are a few reasons why these issues exist. One is the requirement to adapt existing systems. This is just part of policy of the power companies. The second is the complexity. A large number of sensors requires a complex system to manage, read, and take action based on the data read by these sensors. Another is the newness of the systems, with new technologies such as 5G, which allow lower latency and faster speeds. Another is uncertainties in the systems. These may be caused by changes in the environment which don't really exist, but they are read anyway. Another is indecisiveness. This is flip-flopping on decisions made by the sensors that may cause inefficiencies in the system. Related works typically focus on using feedback control loops using the MAPE system. This is monitor, analyze, plan, execute, knowledge. One example of this is the Cosmos Adaptive Service-Based Platform that enables dynamic adaptation to runtime changes to achieve some quality of service requirements. These requirements may be processing usage or response time. These take advantage of layered queuing networks, which will be discussed later on in the video. The problem with these systems is they don't consider the functional goals of the system, and they don't check if these functional goals have been satisfied. This could be how long it takes an actuator to be turned on or off, or how often that actuator is turned on or off. The IAS framework consists of functional and autonomic control elements. Functional control elements are controlled by the functional goals of the system. This can be what actuators need to be turned on or off, or how much current can flow through the system. Autonomic control elements are based on the adaptation goals of the system, which can be resource usage of the system. These are largely affected by the environment, such as when a natural disaster occurs and the response time needs to be immediate. Functional control utilizes the MAPE approach. In this approach, the functional control element monitors data from the sensors, which takes data from the environment that it's in. It then analyzes this data against the functional goals of the system. It then plans the changes that will be made to the devices placed in the environment. It then executes these changes. The autonomic control element also utilizes this MAPE approach. The autonomic control element takes its input from the functional control's output and the architecture variant, which I will discuss in a bit. It then analyzes these with the adaptation goals, which are affected by the environment. It then plans changes to the architecture variant, and then makes these changes. The architecture variant of the system consists of the hardware and software architecture. The hardware architecture is the IoT hardware. This consists of the actuators, switches, sensors, etc., and doesn't really change. The software architecture consists of components and connectors which joins these sensors and actuators. This is what is adapted by the autonomic control element. This is adjusted based on the quality of service required. The three main types of architecture variant are hierarchical, centralized, and distributed. Centralized generally takes in all data and makes decisions based on the collective data. Distributed has different functional control layers for each separate actuator that exists in the system, while hierarchical is distributed but has a central remote functional control which oversees everything. The application of the IAS framework within this paper is the control of a renewable energy system containing wind energy farms. This consists of 35 substations, 30 lines, and 700 megawatt peak wind farms. One situation that may occur is excessive production from a wind farm, such as when a strong wind blows. In this diagram, it shows the wind farm is D. To combat this, we can charge the battery in E, limit the production from the wind farm at D, or we could activate the circuit breaker in the power lines, taking power from the station. Ideally, a combination would be used. This requires collecting the states of all components of the system. This introduces challenges such as latency between sensors and control systems, computation time, as edge processors may not be as strong as remote processors, and local remote efficiency, as we want these sensors remotely and locally to be able to talk as quickly as possible. Proposed architecture for this system is a hierarchical architecture. This consists of a main cloud with distributed controllers that may be changed. There is an autonomic control element within each gateway and each station. The cloud aggregates data from each station and processes this to control actuators. The NASA platform outputs these commands via a RESTful API and uses a MySQL database to store data. This is then presented to the user on a dashboard. The solver within the cloud component consists of a model predictive control system. This collects real-time data from each sensor and uses this to calculate output values. The architectural challenges of this system is maintaining the quality of service required and changing the architecture based on the environment that it is currently in. To do this, we may utilize queuing networks. The queuing network may consist of multiple functional control elements. These may either be local or remote. An autonomic control element at the input does load balancing and decides where data is sent and which functional control element will process it. This data at the output is then collected and used to actuate the system. The benefits of this is more resources, as the remote FCE may have more resources than local ones. It also provides redundancy, as one FCE may go down. This data can then be sent to another one in the system. This is an example of a queuing network for the power transmission network. This queuing network consists of sampling nodes which continuously sample the environmental data. The autonomic control element then balances this data to the functional control elements. This data is queued at the input and is processed at the same time. An autonomic control element is then used to control the actuators in the system. These FCEs may take three modes: fast action, normal, or enhanced forecasting. Fast action is used when the outputs need to be seen as quick as possible, such as in a disaster. Normal is used when the system can act normally and may change. And enhanced forecasting is used when the power of the system can be forecasted in advance and communication times don't matter as much. fork is then used to split the process data from the autonomic control element to each actuator. This is delayed, so all actuators change at the same time. The loop can be considered done when the changes caused by the actuators is sampled again at the sampling nodes. First autonomic control element again utilizes the map case system. The autonomic control element here monitors the situation from the FCEs and adapts the architecture when required. It also performs load balancing, which may be used based on probability, completely random, round robin, the shortest queue or the shortest response time, the least utilization, or the FCE which will process the data fastest. The functional control element of the queuing network also utilizes the mapcase system. This consists of local or central FCEs depending on the architecture being used. There are three modes within these FCEs: fast action, normal, and enhanced forecasting. Fast action uses a simple flowchart to determine the outputs of the system. Normal mode will try and calculate the best use of actuators within the system, but if not able to do so within 60 seconds will fall back to the fast action mode. The enhanced forecasting mode will try and predict future forecasts and power usage. This consumes a high amount of CPU. Fast action is obviously the quickest, with normal, slightly faster, and enhanced forecasting mode taking the longest amount of time. The queuing network implementation was then simulated for each mode, with each mode being run in the centralized, distributed, and hierarchical architectures. It was found that when using the hierarchical for mode 3, centralized for mode 2, and either the distributed or centralized architecture for mode 1, that the system had the lowest response time of 1.66 seconds. Furthermore, it was seen that using only the centralized architecture for all three modes caused a 58% increase in delay. Fault intolerances may also be seen when using only the centralized architecture for all three modes, as one node going down might cause the whole system to go down. Furthermore, increasing the computing power within the distributed architecture causes a significant decrease of 11% in the response time when it is used. In conclusion, the benefits of this system is a reduced response time, the ability to maintain the quality of service of the system, and the increased reliability from having not just a centralized system. Future work that may be undertaken is the formalization of the runtime pattern selection. This is when an architecture is chosen or when it is adapted. Also, the formalization of the sampling rate settings, so the data is sampled in sync and not random. One critique I have of the system is the cost of the system. The system consists of a lot of nodes and a lot of sensors. These all need to be able to talk to each other using gateways and remote servers. This would be a costly exercise. There is also the restructuring of current systems, which have been formalized over the years. Another is the development of the system. This system is complex and will require a large amount of work to be implemented. There is also the integration with existing systems that may not be able to be easily upgraded to the new system. Thank you.